Hello and welcome to this lesson about the probability of multiple events. The learning target for this video is find the probability of independent, dependent, and mutually exclusive events. So first of all, let's talk about some keywords and let's draw a line in the sand. So our first keyword is going to be compound. And what this refers to is multiple events that potentially overlap. And so compound refers to potentially overlapping events. I'll give you an example in a second. Now the other keyword that we have is, well, it's more of a key phrase, mutually exclusive. And what we're getting at with mutually exclusive is that these are completely separate events. Separate events. And the thing is, we need to know what it is we're dealing with before we start to calculate some probabilities, because each of these have a different tactic. All right. Now, an example of a compound event could be something like rolling dice over and over and over again, where we are just doing the same thing time and time and time again. And so what's going to happen is that this probability of rolling the dice is just going to get repeated over and over. And we'll kind of talk about what that looks like in a minute. Mutually exclusive events could be something like rolling dice and maybe like flipping a coin. That may not be the best example to kind of get our heads around it at the very beginning, but we're dealing with things that can be completely separate. Okay, now let's get into compound probability. Here's the rule that we have to know. Let's say we're taking a look at two events, the probability of A and B. It's going to equal the probability of A times the probability of B. All right? And so, for example, let's say that we're going to roll two dice. And we want the probability that we're going to get two, let me write that like this, 2 3s. Okay, well, let's think about it. When we have that first dice, or die, whatever you want to call it, we have 6 options for it. It could be a 1, a 2, 3, 4, 5, or 6. And then the second one that gets rolled has the same options. 1, 2, 3, 4, 5, 6. Now here's where it gets a little bit crazy. When you roll that first one, the second one could be any of these. So just off of that one dice right here, we have 6 potential options. We also have, and then we can repeat that for each of these. We'll have an additional 6. And so what this gives us is essentially 36 different possible outcomes. So if we're looking at that ratio of possible to desired, there are 36 different ways we can do this. And what it boils down to is when we have the 1 3 and the 1 3 going at the same time, which is just there's only one way that works. The first one has to be a 3 and the second one has to be a 3. That is the only outcome that works for us. And so that is 1 out of 36. Well, if we just think about it as like, each one of these individual probabilities, the probability of rolling a 3 on the first dice is 1 out of 6. The probability of rolling a 3 on the second dice is also 1 out of 6. And so we multiply them together, we end up getting that 1 out of 36. Now, this is where we have to read the fine print a little bit. There's a difference between independent events and dependent events. And so I'm just kind of abbreviating that IND and DEP for independent and dependent events. With independent events, the probability stays the same. So for that one, let's use that idea of rolling dice over and over and over and over and over. Every time you roll the dice, especially if you're just looking for one number, you have a 1 out of 6 chance of getting it. And then you're going to times it by 1 over 6. And you're going to times that by 1 over 6. And you're going to keep doing that over and over and over again to find the probability you want. The probability here is staying the same. It's constantly 1/6. Dependent, the probability changes. Probability changes, and what that means is that you have to think about that. All right, so here I'm going to draw, I don't know, a little satchel, a little sack or something, and I'm going to put some marbles in here. We got blue, we got green, so in a red, a couple of reds, let's do one more, perfect. All right, now let's say we want the probability, oops, I wanted to do it in a different color. The probability of getting or I don't know, let's just say the probability of getting 2 reds. All right, so the way that's going to work is, let's see here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. The first one we get, we have a probability of 3 out of 9 for getting a red. A third of those are red. But when we take one of them out, we only have one, or we have 1 fewer in there. So we now have 8 in there. And we'll then have maybe 2 out of 8 as our probability. Now notice how these changed. And that's because our total number of possible things has changed. Usually this will reduce by 1 because you've taken something out. You've now kind of changed the dynamics a little bit for that. So the process, the mechanics is the same. You're going to multiply the probabilities together. So this idea is key. Probability of A times the probability of B. Finally, let's talk about mutually exclusive. If we're kind of looking at written in probability words, it's the probability of A or B. And that's going to be equal to the probability of A plus the probability of B. Now here's the thing. Mutually exclusive means that there's no overlap between these two things. All right? So whatever set A is and whatever set B is, there's nothing they share in common. Now there is a way we can figure out the probability, and I'll show you at the end if there is something in common. But right now, let's just say we're doing 2 things that are separate. So for example, let's say we want to find the probability of rolling a 1 or 6. Now we're happy with either 1 or 6. That's the desired outcome. Well, we have a couple of options. If we look at the probability of getting a 1, that's 1/6. If we think about the probability of getting a 6, that is also 1/6. But these things are completely exclusive. All right, 1's over here, 6 is over there. There's no overlap between them. So what we can do is we will add their probabilities, which is 2/6, which equals 1/3. Now, let's think about it. If we draw this out, we have on our dice 6 possibilities, right? So let's see here. Let's go like that. All right, you're either going to roll a 1, a 2, a 3, a 4, a 5, or a 6. We're happy if we get the 1 or the 6. Well, let's look at that ratio. We have 2 out of 1, 2, 3, 4, 5, 6. 2/6, aka 1/3. So if they're mutually exclusive and there's we're looking at an or situation, you add the probabilities. Now, I'm not sure how much we might come across this because this is a slightly more advanced concept, but if we do not have mutually exclusive, but we're looking at something like a probability of A or B, and then here we'll put where A and B aren't exclusive, we have a slightly different formula. And that formula is, so I'll just write it all out, or P probability of A plus the probability of B plus, or sorry, not plus, minus the probability of A and B. That's how we would figure that out. Now that's a little more nuanced, and that has to do something like, let's say you're messing with a deck of cards, and you want the probability of a heart, or let's say a jack. Okay? Now, we could be happy either way, with a heart or a jack. The probability of getting a heart is, let's see here, 1/4, because there are 4 suits, and there are 13 of each one of them, so it's actually 13 out of 52, which reduces down to 1/4. The probability of getting a jack is 1/13. But here's the thing, there's an overlap. So if we were kind of draw out these sets, we have all the hearts. So that would be like the 1, 2, 3, 4 of hearts, so on, so on. And then we have the jack of spades. Sorry about the spades, awkward drawing. We have the jack of diamonds, and we have the jack of clubs. But then we also have the jack of hearts. And this is also a heart. So there's a little bit of overlap here. So in order to figure out what the probability of getting a jack or a heart or a jack is we would take, oops, let me erase that. We'll have 1/4 plus 1/13 minus 1/52. And then that way we're just looking at, all of these possibilities here, and we're not double counting that one. Now, we may or may not come across that too much, and then we'd have to get common denominators, add, subtract, multiply, all that fun stuff. But I wanted to show you just in case we do stumble across it. All right, so just to kind of recap everything, a couple of big ideas. That's a horrible recap. Let's try that again. We have 2 sort of tactics. We have compound, which is probability of A times the probability of B. They may or may not be the same, so be the same is a question. It depends if it's independent or dependent. If we're talking about exclusive, we're looking at the probability of A plus the probability of B. And sometimes we might have to subtract the probability of A and B if they do overlap. So that's it. Good luck with your homework or practice, and let me know if you have any questions.